All right, today we're going to be talking about electrical wires. We're going to talk about their insulation. We're going to talk about the different sizes. How do we choose a size? That's going to be based off of the amperage that we're using. But we also have to consider, is it a continuous load, right? Because if it's a continuous load, when we're concerned about amperage, the thing that we always are worried about is heat, right? Heat buildup. And so a continuous load, you're going to have less time for that heat to dissipate. And so we're going to have to, have some correction factors in there to adjust how much amperage we are calculating for and to adjust for what wire size that we're going to use. We're going to have to consider the terminations, right, where that wire hooks up into a device. Is that device rated for a certain temperature? And so if it's not rated for a certain temperature, then we may have to derate that wire. We may have to use a larger wire or a different size wire based on the termination where it's going to be hooked up. Um, we may have to derate. I say derate. All of these factors is what used to be called derating in the code book. Now it's been broken down into separate parts for each thing that you do. So like we're going to talk about correction factors for temperature. We're going to talk about adjustment factors for the number of wires that we put into the conduit. And so those are going to be all factors that go into us choosing what wire size we're going to use for a specific situation. Then we're going to work some sample problems together. Hopefully by the end of this, you guys will have an understanding about how all these things interact. There'll be a good bit of flipping back and forth between different tables, and I'm going to have all those tables pulled up in the slides. But it'd be a good idea if you've got a code book to have it out where you can practice flipping through these things, because as an electrician, right, these are things that you're going to be working on a regular basis. So the first thing we're going to talk about is just electrical wire in general. What's it made out of? So electrical wire in the electrical field is made from either copper or aluminum. If you're building a satellite to launch into space, maybe you're using some exotic metals, you're using some gold, you're using some platinum, you're using some things to conduct electricity that are, even better conductors than copper is. But for the electrical field, we're using copper or aluminum. Um, we use those in different situations based on their properties and based on their cost. Um, Copper it's a much better conductor than aluminum. It will also not expand or contract as much as aluminum wire will, which is also an advantage that it has, right? When we're installing aluminum wire into a panel, we have to be careful that we torque those connection bolts down to the proper torque for aluminum, because if we don't, we could have some expansion and contraction throughout the year that could cause arcing, that could cause a fire, right? And that's what we want to avoid. And they think, well, if copper has all these advantages, why don't we only use copper? Why are we not required to use copper all the time if aluminum can be a hazard? And it really comes down to cost. When we get into larger wire sizes, aluminum is just so much cheaper. We can actually have situations where, because aluminum is not as good of a conductor, we have to use a larger aluminum wire to to run to a load than we would if we were running it with copper. And even though we're using a larger amount of aluminum, it's a larger chunk of aluminum in that wire because it's a larger wire. Aluminum is so much cheaper than copper that it still makes financial sense to use aluminum over using copper. Um, and so those are kind of anywhere we're running the main service into a residential home. Most places that's going to be aluminum now, because it's just the cost is just so much cheaper. You can get aluminum for in building sizes generally from about size 8 AUG up to like 1,000 kc mil, something like that. And you can get all wire sizes in copper. we can get, from the smallest up to the biggest, we can get it in copper. We're just, in a lot of situations, we're not using it because it's cost prohibitive. Now, we are required, if we're in a residential situation, once we get to size 8 AUG and smaller, that has to be copper wire. We're pulling copper wire to all those loads, all those receptacles, all those lights. All those are going to be copper in a residential situation. Those smaller sizes, we're just making sure that we're doing those in copper. All right, next we're going to talk about the insulation. And so the insulation that goes on the wire, we have a lot of choices for that, right? We can we want that wire to be insulated well enough to protect it from short circuit, and based on the temperature that the situation that it's going to be in, depending on how much amperage is running through it, we have a lot. There's a lot of options that we can talk about how we can size that insulation or choose that insulation. 310.4 1 and 2 talks a lot about, there's a couple of tables there that talks a lot about the specific insulation types for each wire type, right? And so we're going to next slide we'll talk a little bit more about what those wire insulation types are. But one thing that is, all electrical wire is required to have is it's got to be marked, right? It has to be marked with the maximum rated voltage. It has to be marked with the proper letters for the insulation type. We're going to talk about that here in just a second, right? What that means. It has to have the manufacturer's name or trademark, something that identifies who made this wire, and then it has to have the wire size in either AUGs, which is American AWG, which is American wire gauge, or the circular mill, which is that's the metric wire size. It's got to have all 4 of those things on it so that it can be readily identified as electrical wire, and that you can identify it as the type that you need or that you don't need. Now, when we're talking about those insulation types, we have to choose that insulation type that we want to use for a given area, and we're gonna talk about that at length more as we get into this. But we have to know how to identify that wire type, right? So on the outer sheath of that wire, it's gonna be labeled with a 2, 3, or 4 letter code, and that code tells us what are the properties of the insulation on this wire, right? So if we have no H's in the word, so right, so it's like a SE, right? That doesn't have an H in that name, and that tells us that it is rated for 60 degrees Celsius, right? That's the temperature rating for the ambient temperature that wire can be in without needing some kind of a derating factor, right? It was designed for a 60-degree environment, right? And so if it's got 1H, right, that's a little better, right? It's telling us that insulation is rated for a higher temperature, right? And a higher temperature doesn't just mean the ambient temperature. It also means, right, like that wire, it's got electricity running through it, and that amperage creates heat, and we want for the jacket of that wire not to melt off or not to become brittle. And so when we're choosing wire size, we have to choose it based on the amperage of the stuff we're running through it and the temperature of the surroundings, and we want to make sure that wire is going to be sufficient. And so we also have a high heat, right, wire, which is good for 90 degrees Celsius. So that insulation is a little bit better than the other 2, right? And so you might have something like THHN, right? And so that T stands for something, and then the HH tells you that is a 90 degree Celsius rating. That N in THHN is nylon outer covering, right? That outer covering is on top of the regular insulation layer. It has a smooth coat of nylon, which is just like a slick coat that helps it be pulled through conduit, right? It's an abrasion resistant layer that helps us pull that conduit. Um, R would be thermoset insulation. That's another type of insulation that can be on that wire. T, thermoplastic insulation, right? So that I mentioned THHN. That's one of the most popular wires on the market, right? THHN or THWN-2. Those are two things that you're going to see a ton of in the industry, right? Those are wires that are good for high heat, and they have the thermoplastic has a very malleable insulation that's good for running through conduit with the nylon jacket. It gets used a lot. We'll talk about it a lot in class. We'll use it as an example a lot because it's one that you're going to run into a good bit, right? You can also sometimes I forgot to mention here when we're talking about the HH. Sometimes you'll have a single H, and then at the end there'll be a -2, right? If there's ever a -2 there, it's telling. And if you got an H with a -2, it's telling you there's actually two H's there. So like I don't know why they don't just put two H's in it and make it a 5-letter code. Some of these will be 4-letter codes. Um, Once you get to 4 letters, that's kind of where they cut it off. But sometimes it'll have 4 letters and a -2 instead of just having 5 letters in it. So if you see something that is a THWN-2, right, that is a thermoplastic insulation with high heat insulation because it's got the -2. W means it's good for wet or damp locations, and then N, it has that nylon outer jacket, right? Those are the things that you're seeing in that code that'll tell you exactly what it is. The other things to talk about, right? We got U for underground, right? They make cable that's good for direct burial underground. And then X is cross-linked polyethylene insulation. That's just another one that you will occasionally see, right? These are all insulation types. And if you go back to that, the 110 tables, it'll tell you which, you more detail on what all those insulations are for each specific wire type. You also have non-metallic cable. We're not going to get too heavy into this, right? This is non-metallic sheath cable, I should say. And so this is like Romex, right? So these are all the different kinds of these are wires that it's a bundle of wires, so a cable that's wrapped in a insulated sleeve, right? And so you have NMB. This is standard non-metallic sheath cable. This is Romex, suitable for dry locations. UF, underground feeder cable, right? This is good for direct burial, right? So if you needed to run a receptacle out in the middle of your yard or wanted to have a lamp post out there somewhere, you can direct bury this wire as long as you follow all the rules on how deep to bury it. SE, service entrance cable, right? So that's going to have all the wires that you need are bundled together in a single cable to run into your main panel for the house. And then USE is that same thing, but you got the U, tells you it's rated for underground, right? And so as I said, we've got the example of the THHN wire. It's thermoplastic, heat resistant, up to 90 degrees Celsius or 194 degrees Fahrenheit. Has a nylon outer covering. Electrical wire can be bought in a bunch of different sizes, right? We can get it from down what we call Cat 6, right, which is 24 AUG, up to service entrances, which are 2/0 AUG. If you notice, right, like that number for a service entrance was a smaller number than the number for Cat 6, which is a tinier wire. You have a tiny little wire that's in telephone wire. This is size 24, and then you have a very large wire for our service entrance, which is a 2/0. That doesn't seem to make sense, but our wire sizes they get bigger as the number gets smaller until we get down to 1, and then once we get to 1, then we cross a threshold where we start getting 1/0 AUG, and then 2/0, and then 3/0. They start going back up once we get to that size, and then we reach a certain point, and we just measure them in KC mil. Once they get so big, we just measure them just in the KC the 1,000 circular mils of, we measure it in metric as far as, once they get so large. Um, the different, just some examples of wire that you may have around the house and what size that would be. Most lamp cords are either 16 or 18 AUG, right? So that when I say AUG, right, I'm saying that's American wire gauge, right? We're talking about the gauge of wire that is the size of it. Most home wiring is either 14 or 12, right? If you've got 15 amp receptacles, you may have either 14 or 12 run to those, and then 12 AUG is good for up to 20 amp circuits. Your water heater and your dryer, they may be run on 10 AUG. Stoves could be 8 or 6, right? And so as we go down, right, these wires are getting fatter and fatter as we go down. And so that's kind of how that works. And so then we have to talk about, like, how are we going to choose a size of wire? Well, all right, so if we're going to size a wire, the first thing we got to know is how many amps does the thing have that we're trying to provide power for, right? That's what's going to be the basis of our wire size. And so based on the type of insulation that we looked at earlier, right, the different kinds of insulation have different amounts of ampacity, right? So I can have a wire that is sized as a number 8 wire, right? And that's the actual size is 8 AUG. That is a gauge of wire. And so for all three of these types, that wire size is the same. But based upon what kind of insulation we put on that wire, we have the capacity for more amperage on that wire. Now, there's going to be some things that limit us to that as we move later on, but this shows us what the amperage that wire can handle in certain conditions that it's capable of holding, right? So if we have insulation that is rated for 90 degrees, right? If we look at this right here, it says that if the ambient temperature is only 30 degrees, right? So if this insulation was designed to go up to 90 degrees and the ambient temperature is only 30 degrees, right? That insulation is going to do a really good job of keeping that wire insulated and cool at that much lower temperature, right? So we have some extra ampacity on that same size of wire, even though we have different just by putting it on a different insulation, right? The wire type also falls into this, right? So if it is copper wire, right? This is copper wire. Off to the right on this same table, right? This is only a portion of table 31016. 31016 also has another half off to the right of this that is the aluminum conductors, right? And so with aluminum, it's not quite as good of a conductor. Some of these are gonna be, a size 12 wire on the aluminum side is not gonna hold 20 amps. It's not gonna hold 25 amps. It's not gonna hold 30 amps. It's gonna be a lower number that aluminum is able to hold at certain sizes. So if I need a number, we're using the aluminum for the larger sizes. Generally, we're not using it on the smaller sizes. But so if I needed an aluminum wire that could, hold 50 amps, right? It's not going to be a number 8. It's going to take a larger wire to hold 50 amps on the aluminum side. And then this is only the top half of the chart as well, right? So this goes from 18 down to 1 AUG. This right below this is going to go to 1 AUG, and it's going to start going back up towards the KC mils. So this chart, has, for a lot of different wire types, it has the amperages that we are allowed to use. It's 31016. You see this one is labeled as 310.15B16. There were 2 or 3 years in the code book where they thought it was a good idea to try to break it down because It's similar to the things that are in 31015, so they thought it would be a good idea to break it down like that. It was 310.16 for many years, and I think that they realized that it was just people were having difficulty finding the chart when it was labeled this way, and so it is now 310.16 in the 2020 or newer code book. So when you're needing to find this chart, and this chart will get referenced a lot, right, as we're going through this today, and as you guys move through residential, commercial, industrial, AC/DC machines, conduit bending, we're going to reference this chart, right? Because this is the chart that tells us how many amps a certain wire, a certain size wire can hold with different types of insulation. That's going to be information we're going to use many, many times. Right now we've reached the first step, right? We want to actually size a wire based on an amperage, right? And so the first thing we got to know, what kind of wire we're going to use. Well, if we're going to use copper wire, then this will be the side of the chart that we need, right? And since this is the side of the chart that I've got pulled up, we're gonna assume for this little example that we're using copper wire, right? The next step is going to be what is the insulation made of, right? Our next step is what kind of insulation do we have? Do we have TW, UF, THHW, THHN, right? What kind of insulation do we have, right? The third is we need to know what is the amperage of the load that is connected to the wire, right? So if we've got a 35 amp load, right, then I'm going to need wire that can hold 35 amps, right? Now we're going to, this number 10, right, 75 degree, it will, if we're using THWN, it will hold 35 amps, right? And so we might be okay there, but there's going to be some contributing factors that we're going to talk about here in a moment that can limit which specific wire that we can use. Let's use, for an example, number 8, right? So a THHN, right, which is this up here, THHN, number 8, right? So this is the number 8. It is copper, right? So we're in the right one because we're using the copper, and we need something that's rated for at least 55 amps, right? So that's going to be our 90 degrees Celsius, right? THHN, number 8, copper, is rated for 55 amps. That's what that will hold. So if we needed to know that information, right, this is where we would come to find that information. However, right, this is one of those places in the code book, right, where we start getting into this is the rule, but, right, that number 8, it will hold 55 amps, right, but we're limited by several factors. One of them is the terminal to which that wire is connected, right? So we're not just looking at the wire, what is the amperage of the wire, right? But that wire connects on either end, right? Either end that wire is connected, it's bolted in, it's got a set screw, it's got something that's holding that wire in, right? And so that terminal is rated for a certain temperature, right? And it needs a certain size wire in it. As when it was tested with a certain size wire, and that wire that it was tested with is part of its heat sink, right? It's that larger. It may be whereas you could use a number 8 for the 55 amps because it says that's good. Well, that device that is plugged into, they may have tested it with a number 6 wire, a larger wire, and that number 6 was enough to dissipate the heat that is building up in that terminal, where a number 8 would not be, right? And so we're limited by the size, by the rating of the terminal, right? And so a lot of terminals they don't have a rating on them. A lot of older ones, most newer ones are required to have a rating on them. And in general, they should be rated 75 degrees. But if we don't know, right? If it's less than 100 amps, we have to assume that it's rated for 60 degrees Celsius, right? And so if the terminal on a device is only rated for 60 degrees Celsius, when we choose our wire size, we have to choose a wire size out of the 60-degree column, right? So if I needed that 55 amps, let's go back to that 55 amps, right? If I'm looking for that 55 amps, I have to use this 60-degree column, and a number 8 is only good for 40 amps here, right? And so I have to use a number 6 wire to get that 55 amps. Now, I can still use a THHN, right? Number 6 wire. And so now that insulation rating means that number 6 wire, right, it has an ampacity. It will hold 75 amps, right? Even though I can only put 55 amps on it. I'm limiting myself because of the terminals to only putting 55 amps on it. The wire itself will hold up to 75 amps. And that's important because here in a couple of minutes, we're going to start looking at other things that could derate that wire, right? Like, is it in an environment that has a really hot temperature, right? Do I have a whole bunch of wires stuffed into one piece of conduit, right? And so if I do, if I need 55 amps worth of wire, if I need a wire that'll hold 55 amps, well, if I derate this, if I use a wire that's only at 55 amps, then if I derate that wire at all, right? If I derate it at all down to 52 amps, now that number 6 isn't big enough. I would have to go up again, right? But if I use a better insulation on that number 6 wire, right, then if I have to derate it by 5 or 6 amps, right, now it's good for 69 amps or 68 amps, and it would still be within its realm of it'd be over the 55 amps, so we would still be okay, right? And so anytime that the amperage is less than 100 amps, right, unless I am given if I'm given that the terminations are 75 degrees for all the terminations in the series, right? Like if one of those terminations I don't have a 75 degree listing, right? If one of them is not listed, then I have to use the 60-degree column for that wire, right? It only takes one terminal that's not listed at 75 degrees for me to have to use this 60-degree column. And I'm going to use this 60-degree column all the way up to 100 amps, right? Anything that is 100 amps or less, I'm going to use this 60-degree column to choose my wire size. Now, if it's over 100 amps, then I can use the 75-degree column. And I can use the 75-degree column if it's over 100 amps, because if it's over 100 amps, there is a requirement that those terminals be rated for 75 degrees. Anytime that the amperage that is being the load is over 100 amps, there is a requirement for the UL to list those devices with 75-degree terminals to handle that extra amperage. And so I get to use the 75-degree column on any load that is 100 amps or more. And so that's gonna help us out a little bit when we get to it. May make it a little bit harder on us, right? Because now you've got to remember: am I going to use the 60-degree column? Am I going to use the 75-degree column? And it's going to depend. And that'll be something that we're going to talk about as we're going to take these things slow. We'll work through these, and we'll work a few sample problems together, and hopefully you will understand how this works as we get through here. It'll be something that we continue to talk about. Like I said, this is something that we deal with. Choosing wire size, we choose wire size in residential. We do it in commercial. We do it in conduit bending. We do it in AC/DC machines. We're doing this in all of those classes. There'll be some of this you're going to work on it. And so if this is the first class that you're taking where you're dealing with this, you're gonna get more practice with this, right? Because we're gonna work on it, and hopefully, you'll understand it this first time through, and you'll just get better at it and better at it as you continue to work on it. As an example, we have a 50 amp device, and it has 60-degree rated terminals. So when we're choosing our wire size, we're going to use the column for the 60-degree Celsius column. Now, if we look at that, right, we need, if we've got 50 amps, then we need 50 amps, So we're going to come down and we're going to find the smallest wire that is good for at least 50 amps. And that's going to be the number 6. And so with the number 6, we're going to be okay with the number 6 because it's good for 55 amps at 60 degrees Celsius. What we can't do is come over to this column right here and say, well, I'm going to use better wire. I'm going to use THHN wire, which is rated for 90 degrees, and a number 8 wire will hold 55 amps. Well, this device wasn't designed to hold a number 8 wire. This device was designed to hold a number 6 wire. And so in its design, part of its design characteristics may be that it requires that larger size wire to remove the heat from the device. And so if we use a smaller size wire, while the wire could possibly handle that extra heat because it has the better insulation, we can't be sure that the device can handle that extra heat because the device was designed for the larger wire. And so in this case, right, we have to use a number 6 wire. And we could use THHN wire, but if we use THHN wire, we have to use the number 6. And it would be good for up to 75 amps, which is overkill. But overkill is fine because we're gonna talk about here on the next page things that might cut back on that 75 amps. We may not be able to use that full 75 amps. But we obviously can't use the full 75 amps because we're limited to, we got a 50 amp breaker, but we may have some things that cut back the amount of amps that we're allowed to use, and we may cut it back so far that we actually have to up the size of wire, right? If our derating factors cut back the amount of amperage that we can use enough, we would actually have to choose a larger size wire. All right, before we move on to looking at what those derating factors are, those correction factors are, we're going to take a moment to look at one more exception to when we're choosing our wire size. That being that 18 through 10 AUG have these little stars beside them. And if we go down to the bottom of the chart, there is a note that says refer to 240D. And if we flip in our code book over to 240D, we'll see it says that the overcurrent protection shall not exceed 15 amps for 14 AUG, 20 amps for 12 AUG, or 30 amps for 10 AUG. And so if my overcurrent protection on a 14 AUG wire is 15 amps, I can't put more than 15 amps on it. Even if I have 20 amp wire, right? If the overcurrent protection is set to 15 amps, well, it's going to trip if I put more than 15 amps on it. And so this this is just another little exception that we have to be aware of. And it doesn't actually change anything that we talked about in the last segment, right? Anything less than 100 amps, we're choosing wire from the 60 amp column. And so that 14, 12, and 10, that is 15, 20, and 30. That's what it says that we can use right there. So like we look at an example here, number 14 wire, it has a 15 amp breaker, so I'm going to be limited to putting 15 amps on it. Doesn't matter if we have the higher rated insulation. So now we have to start talking about things that are going to adjust the amperage load that I'm allowed to put on a particular wire. So the first of those things that we're going to talk about is continuous loads. And so this is going to actually adjust the amperage that we use for calculating our wire size. Section 219A1 says that where a branch circuit supplies continuous loads or any combination of continuous and non-continuous loads, that the minimum branch circuit size before the application of any adjustment or correction factors, it shall have an allowable ampacity of not less than that of the non-continuous load plus 125% of the continuous load. Okay, so what that means is, right, if we have a continuous load, and a continuous load is what Article 100 in the code book defines as a load that's running for more than 3 hours in a row, right? So in the South, right, you're talking about air conditioners. You could be talking about, if it's a commercial building, the lighting is going to be on for 8 to 10 hours a day. Those type of things. Something's going to be on for, if it is on for more than 3 hours in a row, if it's expected to be on for more than 3 hours at a time, then we're going to take that portion of whatever that branch circuit is, right? So if I've got more than one thing on the branch circuit, I don't have to multiply the entire thing by 125% or 1.25. I only have to do the portion that is going to be over, there's going to be a continuous load. The part that is going to be running for 3 hours or more, that amperage I will need to pad by an extra 25%, so that, when we're talking about amperage, we're concerned about heat. And so any device that runs for a short time and it builds up heat and then it shuts off and it has time to dissipate that heat, right? We're not having to pad those numbers. But if we have a device that there is the potential for, as it's running constantly, it builds up heat in that wire from that electricity, that amperage running through that wire. If we don't give that wire a chance to dissipate that heat, then we're gonna pad the amperage that we're using for choosing the wire size. Now it's like, if it's a 10 amp motor, it's only using 10 amps, right? But we're gonna choose a wire that's good for 12.5 amps, so that it has better conductive qualities, so that we don't build up too much excess heat. So we got an example here. Let's look at our example here. We've got a motor that will run for 2 hours a day at 10 amps, right? That'd be 10 amp. That'd be a 10 amp load, right? We do not have to multiply that by 125% or 1.25. So we have a motor that is a 10 amp load. We would choose wire that was good for a 10 amp load. If that motor was to run 10 hours a day, right, and it's a continuous load, we're going to take that 10 amps and then multiply it. We have one motor times 10 amps times 125%, or 1.25, and you're going to get 12.5 amps. If you had these two loads together, right, you have your 10 amp load and you have your 10 amp load continuous, we add those together, we get 22.5 amps. And so if both of these motors were on the same branch circuit, I would need to choose wire that was suitable for 22.5 amps. All right, so now we've picked us out a wire size based on either the 60 or the 75 degree column, depending on the temperature. We have also padded that amperage, right? So before we picked that out, we actually padded that amperage to say, this is a continuous load or not. If it is a continuous load, then when I choose that wire, in that last example, 22.5 amps, I'm choosing a wire good for 22.5 amps. That's less than 100 amps, so that's going to come out of the 60 degree column. I'm going to be choosing a wire out of that column. And so when we look at this, we have to be aware that we're now going to be using something called adjustment factors and correction factors. This used to be called derating. You may still hear somebody on the job site calling it derating. All that means is we are factors that are going to reduce the amount of amperage we can put on that wire. So here's where using that wire with better insulation will come in really handy, right? Because if we use a wire with a better insulation, we chose the wire on that 60 degree column, and say it was good for if we're looking at our last example, the 22.5 amps, that's going to be a size 10 wire. Is good for up to 30 amps. But over in my other column, for the better insulation, it's good for more than 30 amps. And as I start to derate these things, I can derate in the column of the type of insulation it is. And as we are using these adjustment factors and bringing down the amount of amperage that we're allowed on that wire, as long as it's still at the end has enough amperage for the wire that we're choosing, then we're still good. So our first thing that we're going to look at is what we call adjustment factors, right? So this is for the number of current carrying conductors in a raceway. So we just talked about with continuous loads, heat buildup. If I have 10 or 12 or 15 wires in a piece of conduit, and each one of them is generating just a little bit of heat, and they're all bundled together, that heat can build up, and it can cause insulation breakdown. If the insulation breaks down, then you can have two wires that come in contact with one another, and that's going to cause a electric shock, and or a short circuit that could trip a breaker, and it's going to you're going to pull all your wires again. So we have in the code book we've got a chart 31015 C1, right? And this chart it gives us if we have 4 to 6 conductors, we're gonna derate or adjust the amount of amperage that wire can hold by 80%. And so when we're counting our wires, we're going to count all the current carrying wires, and that includes our hot conductors and our neutrals. For the purpose of this, even though the neutral is not going to be carrying that full current, it can be carrying a portion of that current, and so we're going to consider that as one of our current carrying conductors when we are counting these wires. We're not going to count any ground wires in this, and so as an example, right, I've got 3 circuits that share a neutral and a ground, right? So we're going to have 4 current carrying conductors. If we are using wire, if they're 20 amp circuits, those are 20 amp circuits. So we're using a wire that's rated for 20 amps. 20 times 0.8 is 16 amps. That's all that I'll be able to put onto that wire, right? So if I were looking for a circuit that was a 20 amp circuit, then instead of choosing wire, right, I choose a wire that's a number 12 in our column for the 60-degree column, and number 12 is good for 20 amps. But if I chose insulation that was better insulation, if I choose the insulation in the THHN column, then that wire is good for closer to 30 amps. And then I do this same calculation. I can do my 30 amps times 0.8, right, and it's still going to be over 20 amps. So that wire would hold what I'm looking for on that 20 amp circuit. So the next factor that can adjust, or that we can use as what we call a correction factor, more derating, 31015B 2A, that's what that chart's called. Like, you're going to find it in 31015. If you go to 31015, you flip a page back and forth, you're going to find these charts. You're going to find the one for adjustment factors, for the number of wires in a conduit, and for the temperature derating. And we have to do both of these, right? You can't just do the one or the other. You got to do both, and they compound each other, right? So you're going to use one and then the other. So in this one, we're going to take our wire type, and this one has a column for each insulation type. And so if we have a THHN wire, right, and we're looking to make it grow in, or see where what our correction factor should be if the ambient temperature is 86 degrees Fahrenheit. I'm going to look in the 90-degree column for THHN, and it tells me that at 86 degrees Fahrenheit, I don't have to have a correction factor. My correction factor is 1. So, 20 amps times 1 is still 20 amps. Now, If that temperature is, say, 120 degrees Fahrenheit, well, now I'm only good for 0.82 of what that wire could hold before. So 20 times 0.82, I get 16.4 amps, right? Now this one, it works both ways, right? So if that wire is going to be in an environment where it's going to have a constant temperature, a constant ambient temperature that is less than 85 degrees, less than 78 degrees, I think it's 78 degrees, I'm going to get to bump up my numbers a little bit. So if I've got a THHN wire rated for 20 amps and it's going to be in 32 degrees Fahrenheit, well, I can come up here, and if it's 50 degrees or less, I can now multiply that by 1.15 to get, I'm allowed to put 23 amps on that wire. Now, I'm going to be limited by the breaker and other factors, but I get to pad this up so that if I've got a bunch of these stuck in a single piece of conduit and it gets padded down, right, those things can counterbalance one another when I'm choosing my wire size and choosing my insulation type. All right, let's work some examples. All right, so let's say I've got 16 lights in a storage room and each one draws 1 amp. The lights are on a motion sensor and the room is rarely occupied. So what that tells me is I'm not going to have to consider this a continuous load because those lights are not on unless someone's in the room. It's rarely occupied, so we're gonna assume that it's not running for 3 hours at a time every day. The ambient temperature in the room is 78 degrees. So if it's 78 degrees, I can look over here and I can see, okay, I am not going to have to do any kind of adjustment factor for a correction factor for my temperature. And that the 2 THW current carrying wires feeding the circuit are the only wires in the conduit, right? Okay, so if those are the only wires in the conduit, I don't have to worry about adjustment factors for the number of wires in the conduit. And so that just leaves me with, it's THW wire, it's 75 degrees Celsius wire, but if it's less than, we're talking 16 lights at 1 amp each is 16 amps. And so if it's 16 amps, that's less than 100 amps. We're choosing our wire out of this column. 16 amps is bigger than 15, so we can't use number 14. We're going to use the number 12. So we're going to use 20 amp wire number 12. Since there are no correction or adjustment factors to adjust what we need to do, 12 is going to be the correct choice for this circuit. And so that's the wire that we're going to choose for this circuit. Okay, let's work as another example, right? So I have a circuit that has 3 lights that run 2 hours a day, 4 lights that run 10 hours a day. Each light is drawing 2 amps each. So they're pretty bright lights. The temperature in the area is 88 degrees, and the feed in the conduit has 4 current carrying wires total. And I'm going to choose a wire that has THHN insulation. Okay. So our first step is find out how many amps we need with our correction factors. So I got 3 lights that don't have a correction factor. They're just 3 lights times 2 amps. That's 6. I have 4 lights times 2 amps. That's 8 amps times 125%. Gives us a total of 10 amps. So when I add those together, that's my total amperage that I'm going to need for this circuit. That's going to be a total load of 16 amps. And so number 14 is not big enough. We're going to be using the size 12, right? It doesn't matter that a size 14 THHN is 25 amps. If it's less than 100 amps, I have to use the 60-degree column when choosing my wire size. And so we're choosing this size wire, which is a size 12 wire. But we are choosing the THHN because it's going to give us 30 amps to work with to begin with, and we're going to use some adjustment correction factors to adjust that 30 amps. So the first thing we're going to do is if we're using a 12 AUG rated at 30 amps, we're going to have to derate for temperature because our temperature is 88 degrees. And so if our temperature was 88 degrees, our average temperature is going to be 88 degrees, then I have to use the 0.96 times my 30 amps. I'm now at 28.8 amps. I hope you guys can see that, right? If you guys need to pause it so that you can look at it and take a look at that, anywhere through here you need to pause it to take a look at these. Take your time to see exactly how these are going, because the ones in your test are going to work just like this, right? All right. So now also, we've looked at temperature. We had 4 current carrying wires in the conduit, and so I'm going to look at my adjustment factor if I have 4 more wires, which is 80%, 0.8. So I'm going to take that 28.8 amps. I'm not taking the 30, right? I'm taking the 28.8 because these are cumulative. They build upon each other, right? We took our continuous duty and bumped up the amperage that we needed, and then we chose a wire for that bumped up size, and then our temperature derated that, and now we're from that previous derating, we're gonna go farther. So I take that 28.8 amps and I multiply that by 0.80 or 80%. I get 23.04 amps. Now, 240.4 says a 12 AUG wire has to be on a 20 amp breaker, and my calculated load is 16 amps. By choosing a 12 AUG wire with 90-degree insulation, we did not have to go to a larger wire size after all the adjustment factors, right? So we got our 20 amp breaker, right? This here is on a 20 amp breaker, and our total here came out over 20 amps. Now we're not drawing 23.04 amps, right? All these calculations that we've done are telling us how many amps are allowed on that wire. And so we are, for a THHN wire, after our correction factors, we're allowed 23.04 amps. Now, because I can't put that, I don't have a 23.04 amp breaker, and I'm not allowed to use a 23.04 amp breaker. I'm only allowed to use a 20 amp breaker. As long as this number is bigger than what our breaker and our load are, we're okay. So we've accomplished what we needed to accomplish here. All right, so we're going to work a couple more examples here. You may notice the longer this video gets, the bigger my hair is getting. It's a lot of material. I understand it's a lot of material, but all of it works together. And so if we try to take these things one at a time, they don't mesh together the way that we need them to mesh together, because all of these are factors that are going into choosing our wire size. Now there's going to be a couple of other factors we're going to have to talk about later on that could adjust these, but there are things that are kind of after the fact that are going to adjust this after we've already chosen our wire size. We may have to look at voltage drop, if we've got a long run, we have to look into that. But for now, this is going to get us all of these things that we're talking about today. It's hard to choose your wire size without talking about these things, because I don't want to teach you, okay, this is the way that you're going to do this, and then be like, oh yeah, except for unless it is that perfect temperature of 78 to 86 degrees, you're going to have to adjust it, or you have only put 3 wires in your conduit, which is not an efficient way of working, right? Like we're going to be pretty much always doing one of those two things, and so it's a lot to put together, but they all work together. So we're going to just work a couple more examples. Hopefully by the time you guys get through those, you'll either know it or you'll know what you need to come to me and ask questions about in class, right? If you need to come and be like, hey, I don't understand this part of it, then we can work a couple of examples on that to see if we can help you out there. All right, so I've got a three-phase continuous duty motor drawing 40 amps. It is supplied by 4 current-carrying THHN conductors in conduit, and the ambient temperature is 88 degrees Fahrenheit. Now, if you notice on this one, I didn't give you none of the stuff's on the slide already. We're going to go through it as we go through. If you want to stop this one here and see if you can figure out the problem, work the problem as a practice problem, and then we're gonna talk about it there, right? And so if you want to take a moment to do that, right, you're more than welcome to. First thing to look at, it tells us it's continuous duty, drawing 40 amps. Now, that doesn't mean that the 40 amps is the continuous duty, right? It's drawing 40 amps. And so when we talk about continuous duty, that rating, that extra 25%, which is going to be here 50 amps, it's not drawing 50 amps. This motor's not drawing 50 amps. The motor is drawing 40 amps, but we're going to select a wire based on 50 amps because that continuous duty is creating a little bit of extra heat, and we want to choose a little bit bigger wire so that we can make sure that we are adjusted for that temperature difference. So that was our first step, right? We have chosen a 50. We know that we need to choose a wire for 50 amps. So, okay, so let's choose a wire. It's less than 100 amps, so we're using the 60-degree column. If it's less than 100 amps, we use the 60-degree column. We need a wire that is good for at least 50 amps. So that's going to be the number 6, right? Our number 8 up here, right? THHN. It says we're using THHN. It says the number 8 is good for 55 amps, but we cannot use this. We cannot use this column when we're choosing our wire size. We got to use this column for choosing our wire size. So we're using the number 6. Now we're still using the THHN because we want for as we do these adjustment factors to still be padded enough for it to work. So the smallest wire size is adequate is the 6 AUG, right? 6 AWG, American wire gauge. That'll be on your test. So American wire gauge, AUG. That's how we wire sizes, how we size wires. Yeah, you got it. So 6 AUG THHN is good up to 75 amps, right? So if we are using THHN, then for our calculations for correction factors and ambient temperature and adjustment factors, right? We can use this column for that, right? Because like that wire itself, it is good for 75 amps, right? Even though we're limited to 55 amps, right? Like it's been designed, if we use THHN, it's been designed for 75 amps. So now let's look at our first correction factor here, right? So 75 amps corrected for temperature. So our temperature here, it says, is 88 degrees Fahrenheit, which is going to be this column right here. So that's going to be times 0.96. So 75 amps times 0.96, 72 amps, right? Okay, so we've got 72 amps. We still have to do the next section. It says we have 4 current carrying conductors. 4 current carrying conductors. We're going to have to use an adjustment factor of 80% if we've got 4 current carrying conductors. So we take that 72 amps. We're not taking the 75 amps. We're taking like these compound upon one another. So if we've already reduced down to 72 amps, now we take that 72 amps and we're going to multiply it by in this column by times 80% to get 57.6 amps. Now, it shouldn't matter which one of those you do first, right? When we're doing multiplication, right? Because you're multiplying the times 0.96 and then you're multiplying that by the 0.80. Any order that you put those in, it should work out the same. But we're going to do ambient on the ones we're going to do ambient temperature first. Then we're going to add on the adjustment factors. I believe that's the way that it's done in the code book. So 57.6 amps. That's what we get after our 2 derating, our correction factor and our adjustment factor. We have made both of those adjustments. It says 57.6 amps. Now that means that wire can still, it's still good to hold 57.6 amps, and we only need it to hold 50 amps. It's only drawing 40 amps. We do need for it to be as big as what our correction factor tells us that wire needs to be. So it does need to be at least 50 amps. And 57.6 amps is larger than the 50 amps we calculated, and so we're going to be allowed to use that size of of wire for that particular load, right? I'm not looking at the breaker, right? Because when we're dealing with motors, you guys get into AC/DC machines and commercial. When we start talking about motors, my breaker may be much larger than 55 amps or 50 amps for a motor that's running, right? And so we're looking at the load. 50 amps is the calculated load that we need to match. We've got overkill for that, which is what we were hoping. It's why we chose the THHN, right? This is why you choose the better insulation, because if we had chosen something out of this column over here, if we had chosen a TW or a UF that was only good for 60 degrees and it was only good for 55 amps to start with, after I did these two derating things, that wire wouldn't have been big enough. We would have actually had to up the size to another size wire, and we were not looking to do that. All right, so one more time, we'll do one more motor here, and this is our same motor. We're using that same motor, that same 40 amp motor, still a continuous duty, except for this time we have 7 current carrying wires in that conduit, and the ambient temperature is up to 107 degrees Fahrenheit, right? So it's the same motor, we just put it in some different conditions. Well, I've given you the moment till you can pause the video here and work this one out if you want to work it out. And then 40 amps times 125%, that's still 50 amps, which means still less than 100 amps. We're still using the 60 degree column. Our number 6 is going to be good for 55 amps. That's going to be the wire that we choose for this. This will be the wire we initially choose for this before we start getting into ambient temperature and adjustment factors. So our first step, right? We're going to adjust for the ambient temperature. 75 amps corrected for temperature is, let's see, 107 degrees. That's going to be this column right here times 0.87. 75 times 0.87 is 65.25 amps. All right, so we've already lost pretty close to 10 amps worth of capacity for this. Now our next step, right? We're just going to take that and we're going to look at our adjustment factor. So our adjustment factor for, 7 current carrying conductors? 7 current carrying conductors is going to be 70%. So 72 times 0.7 or 72 times 70% gives us 45.67 amps. Now our calculated amperage that we need for that wire is 50 amps. So although it is over 45.67 amps, that is over the 40 amps that the motor is actually drawing. Because it's continuous duty, we have to select a wire that's good for at least 50 amps. And this wire, after our derating process, after looking at correction factors and adjustment factors, it's no longer good for 50 amps. It's only good for 45.67 amps. And so we would need to go back in and choose the next wire size up in this condition, or we need to make some other changes. We've got to figure out somewhere else to make a change, right? Run the wire through a different conduit. Something has to change. A variable has to change. Air condition the space. Some kind of variable has to change or we have to choose a larger wire size in this. All right, so that concludes this presentation here. just in general, looking at it, right? When we're choosing our wire size, first thing we've got to look at, is it a continuous load? If it's a continuous load, we've got to pad that by 125%, right? Then we have to make our initial selection of a wire size. And we didn't do an example of it, right? But if it is over 100 amps, then we can use the 75-degree column for choosing our wire size. And there'll be a couple on your test that are probably pulled out of that column. And then if it is less than 100 amps, then we're going to choose the 60-degree column. We're going to find our initial wire size in that column, and then we're going to we've already done our padding for our continuous load. So then we're going to look at the ambient temperature, and we're going to do a ampacity correction for temperature. And so based on what the ambient temperature is, if it is anything other than 78 up to 86, if it's anything other than that, then we're going to have to make a correction, one way or the other, right? We may correct it as less ampacity, or if it's a cold environment, it's possible that we could add some ampacity. Then we're going to look at how many current carrying wires are stuffed in that conduit. If it is more than 3, then we're going to have to make an adjustment. We're going to have to decrease the amount of amperes that we run through those wires. And so, when we're running conduit, we got to be aware of that, right? So, like if we're running conduit for, to a device, or we're running conduit, along the side of a machine, and it's got a lot of, there's a lot of different processes going on there. We got to be aware that if I stuff if I use a piece of 4-inch pipe and I stuff that full of number 12 and number 14 and number 10 wires, I get, probably get a couple hundred in there. But when you're stuffing that many in there, I'm having to derate those wires to such an extent that it's probably not worth it, right? Like it's going to be more advantageous for me to use smaller conduits with a limited number of circuits in each one of those conduits when I'm choosing to run these wires and these circuits from one place to another, so that we don't get into situations where we've created an overheating situation. If you've got any questions, reach out through Blackboard, send me an email, see me in class. Right, we will continue to talk about these things in class. Right, this should get you this is a better job of teaching it than I probably would be able to do in class, because I had the time to really go through each slide slowly and carefully. If there's one that you're stuck on, if there's something that you don't quite understand, I'm happy to we can continue to talk about it in class. Until you get to where you get it, so that you're ready for the exam.